So this is 3.2, complex numbers, part 1. What you'll learn, you'll be able to define and use the imaginary unit I, add, subtract, and multiply complex numbers, find complex solutions and zeros. So we have this thing that we run into a problem, right? When we're solving x squared equals a negative number, we basically have to quit because we can't do that. Nothing squared will give us a negative number. So in a way, we say this has no solution, and it's true. It has no real solutions, okay? So not all quadratic equations have real number solutions because the square of any real number is never a negative number. We know that. We're not allowed to do that, are we? To overcome this problem, mathematicians created an expanded system of numbers using the imaginary unit I, okay? Yes, it's an imaginary. It's not made up, that kind of thing. I mean, someone made it up, but it helps mathematicians get around that fact that they had to take a square root of a negative number, because at that point, we'd have to just quit. We couldn't do anything else. Even if we end up squaring it later on and end up undoing what we just did, anytime you ran into that one issue, you had to just throw your hands up and quit on the math problem. So they designed the imaginary unit, and I is equal to the square root of negative 1. Okay? You might want to write that down. Let me highlight that. Let's do a different color. Okay? That's an important part. And if you square I, square root of negative 1 squared is just negative 1. So those are the two things we're going to use, using that through this lesson. The imaginary unit I can be used to write the square root of any negative number. Okay? So this is the box that kind of sums everything up and gives you an example. So if r is a positive real number, then the square root of negative r is I square root of r. We just bring that negative square root of negative 1, or square root of negative 1, outside of the square root as an I. We separate them. If you end up squaring an I squared ends up being negative, and you can simplify it that way. So let's just jump in and do some. Let's look at example 1, part A. Find the square root of each number. Now we're going to write this out the long form. You do not have to write it out this way when you do it for yourself. But if I write this out like this, that is negative 1 times 25. And I can break that down to the square root of negative 1 times the square root of 25. The square root of negative 1 is I. We know that, okay? It is I. So this is I. The square root of 25 is 5. So we usually write this like we do variables, okay? We usually list them last. Unless it has a square root, then we list them in front, because if you put it after the square root, it gets kind of confusing what's inside the square root, what's outside the square root. So this one, I would write this as 5i. So let's look at B, square root of 72. So I'm going to break this up just like I did before. So the square root of negative 1 times, now let's think about 72. Let's do a little factor tree over here with 72. 72 is 36 times 2, and 36 is 6 times 6, right? Now I can break 6 down to 2 times 3, but I know 6 times 6 is 6 squared, so I can undo that. And you can take shortcuts like that if you would like. So this is 2 times 6 times 6. So the square root of negative 1 times the square root of 2 times 6 times 6. The square root of negative 1 is I. And these 6's, they come out, right? 6 times 6 is 6 squared, and the square root of 6 squared is just 6. So this is 6. And then left behind is just the square root of 2. Okay? So this is a lot of radical work. All right, it's all the square root work. When we're looking for square roots and simplifying, we're looking for pairs. Multiplication under the radical, the pairs, two numbers that are the same. That means they're being squared. Okay? So let's look at C. C we have negative 5 times the square root of, now break this up, negative 1 times 9. So this is negative 5 times the square root of negative 1 times the square root of 9. Okay? Negative 5 is just there. Square root of negative 1 is I. The square root of 9 is 3. Okay? This is all multiplication, so it doesn't matter the order. So let's put all our numbers together. We can multiply negative 5 times 3 is a negative 15i. And then I goes on the end. Just keep it there. It's kind of like a variable. Behaves the same way. Type like terms, that kind of thing. Okay? But it's an actual number. It's the square root of negative 1. Okay, let's take a look at the next part. A complex number written in standard form is a number a plus bi, where a and b are real numbers, and a is the real part, and bi is the imaginary part. Remember, I'm not sure if we did it this year. I think we did it last year, but the real number system. Okay, you have real numbers and you have imaginary numbers. If you look over here, it's a visual of this. So these are all like the numbers we're used to using, like 1, 2, 3, square root of 2, pi. Even though it's irrational, it's still a real number, okay? And you notice the I part is always 0. So these are the real part. The imaginary part, you're actually going to have a value with the I value, with the I. So you're going to have an I value, okay? And it's a number plus some number times I. It could be 1, it could be 3, it could be negative 5. Now, pure imaginary numbers, they are lacking a whole number part. Okay, there's no real number part. Here's the real part, here's the imaginary part. So the pure imaginary numbers is lacking that real number section. Okay, so it's just some number with an I in it. That's it. Okay, so examples of those is negative 4i and 6i. So let's take a look. Let's do, I don't think, yeah. Examples on the next page. So let's take a look. Two complex numbers, a plus bi and c plus di, are equal if and only if a equals c and b equals d. What does that mean? That means that they are equal if these two are the same and the b's are, and the d's are the same. So those have to match up. These have to match up. Okay? If they don't match up, they're not equal. So let's take a look here. Find the value of x and y to satisfy the equation. 2x minus 7i, so 2x, oh, oops, that's a highlighter. 2x minus 7i is equal to 10 plus yi. All right, so we have a real part and an imaginary part. Each one has both of those. So this is the real part, imaginary part. Real part, imaginary part. For these two to be equal, 2x must equal 10. So we're going to set up a small little equation. So 2x must equal 10 for this to be true. So we're going to divide by 2. So x must equal 5. So there is one of the answers for that. Okay, if that's true, the real number part will be equal. Now, the second part, negative 7i must equal yi. These two must be equal. So we're going to set up another small equation. Negative 7 must equal the y part. We don't have to put the I. We know it's the imaginary numbers here, okay? They both have i's in them. So negative 7 must equal y, and that's actually an answer, right? We didn't have to do any kind of math there. So y equals negative 7. So there are your two solutions, okay? X equals 5, y equals negative 7, and if you check that, you can plug them back in and see if they come out to be the exact same thing on both sides. And they do, okay? They do. All right, so let's take a look. Operations with complex numbers. We're just going to be adding and subtracting today. So we'll do the rest of it tomorrow. So the thing, when we multiply or when we add or subtract complex numbers, we add the like terms. We add the real parts and we add the imaginary parts. That's all you have to remember, okay? It's just like variables. If it has an I with it, you can only add it to other I's, add or subtract it to other I's. If you're adding real parts, like just a number, you can add it to other real numbers, okay? So it has to be the same type of number. All right, so let's take a look, or subtraction. And don't forget, when you're subtracting a quantity, you have to distribute that subtraction. That's all, okay? We know how to do this. We're just applying it to complex numbers this time. All right, let's take a look. So let's do A. So 8 minus I plus 5 plus 4I. Now, we're just going to add like terms. So the real parts are 8 and 5. What's 8 plus 5? Is it 13? So 13. And then we're going to add our imaginary parts. So negative I plus 4I is 3I. And there's your answer. Pretty straightforward and easy, right? Let's look at B. Okay, now this one's subtraction. And we have a subtraction in the middle of a set of parentheses, so it means we have to distribute the subtraction. So we have 7 minus 6I minus 3 plus 6I. Add like terms. So our real part is here, is the 7 and the negative 3. 7 plus negative 3 is positive 4. Then we're going to add our imaginary parts. Negative 6I plus 6I is actually 0. So there's no more I values, okay? So the imaginary parts are gone. So we just have the answer of 4. That happens sometimes. So let's look at C. We have 13 minus 2 plus 7I in parentheses plus 5I. So we're going to have to distribute, folks. Okay, so we got subtraction in front instead of parentheses. So we're going to distribute the subtraction. So we get 13 minus 2 minus 7I plus 5I. And now we need to add like terms. The real part is 13 and negative 2. And that is 11. The imaginary part is negative 7I and positive 5I. And that'd be negative 2I. Which is your final answer. All right, so we got one more example, I think. Yeah. Solving real life problems. Okay. So I don't know a whole lot about electricity. Some of you guys might, I do not. Okay. But regardless, we can still answer the question. Electrical circuit components such as resistors, inductors, and capacitors all oppose the flow of current. The opposition is called resistance for resistors and reactance for inductors and capacitors. Each of these quantities is measured in ohms. The symbol used for ohms is that Greek symbol. It's a capital letter Greek omega. Okay? The higher level up you get in math, the more Greek symbols get introduced. All right, so this is like a table. Oh, I meant to use that. This is a table of the variables that they use. This is a picture of a circuit, alternating current source, and yeah. So the table shows the relationship between a component's resistance or reactance and its contributors to impedance. A series circuit is also shown with the resistance or reactance of the component labeled. Well, I didn't copy the question down. Whoops. The impedance for a series circuit is the sum of the impedances for the individual components. Find the impedance circuit value. So notice how these have I's in them, okay, and that's the biggie, okay? So I'm going to read you the question. I'm sorry I forgot to put it in the guided notes. That's okay, we can get this, okay? So, we got in the picture. Never mind, the picture. All right, so we have, let's take a look. This is the resistor. So that's this thing right here. That is 5 ohms. Notice how it doesn't have an I value with it. Okay, so we're just going to take the 5. So I'll color code it too. That'll make it easier. The inductor looks like this, and this is the inductor. So that is an I value. See how the I value? So I value, so this is plus 3I. Then we have the capacitor, which looks like this, which here that is, it's 4 ohms. So, and it's the negative of that. So it's negative 4I. So minus 4I. And we add like terms. So 5 is the only real number. We got 3I and negative 4I, so it's minus 1I. And so the impedance of the circuit is 5 minus I ohms, O-H-M-S. So there's your answer. It's kind of weird. I don't quite understand it. I'm not an electrical person. But if you're interested in electrical engineering, I'm sure that made complete sense to you, or will eventually, okay? So that is all the notes. You do have an assignment on big ideas. There are several problems, but they're super quick and easy, okay? If you have any questions, the conference will be on the entire time, all right? Good luck, and I will see you tomorrow if you don't have any other questions. Bye.